This is Benzene Clayton back again, doing problem number 27 on practice exam 6. Here you look at this problem. If you got to this problem on the test, you would probably say, what the heck is this? This is reactions that we went over way back a long time ago in chapter 18 and 25 when we covered exam number 2. And the reason for questions like this is to make sure that you're still reviewing all of your past reactions. Remember, the key to organic chemistry is just memorizing all of the reactions. And there's some other things like naming and miscellaneous spectroscopy, but it comes down to about 80% of the exam will be reaction after reaction after reaction. So here there's many different ways to memorize reactions. Not only memorize, that's just the very basis, but you have to think through problems. You won't be able to think through problems if you haven't memorized. So let's look. Here we have the reaction tables. They're somewhat helpful. All they are just really just summaries of everything we've done. The best thing to do, though, to make sure that you've actually reviewed and really thoroughly know your reactions, is to use the blank sheet of paper method. So it's one of the best methods of learning. I've read numerous educational articles here that discuss you learn a lot more if you write it down. Getting the information from your brain to a pencil is more complicated than you think, and it will help you in the end in memorizing. And it will help you see what is not in your brain. So I've emphasized up to this point here doing reaction after reaction, but that it's not the only way to memorize. What you can do is look at your list of reagents. You go through and look at the reagents listed here. Say we're on the benzene chapter now. So you can even go here to your blank sheet of paper. We're doing reactions of benzene. You can start out easy and draw your benzene and then list the reagents. While you're looking at your reaction table, maybe you don't memorize exactly every single detail of the reagent. It actually helps if you write it out like this. You don't have to use your left hand unless you are left-handed, but your right hand is generally sufficient too in memorizing. So just look at the tables, list out the reagents directly from the table. Right here. H2SO4, a little bit of nitric acid. You go through the list. Next one is SO3, a little bit of sulfuric acid. This is the fuming sulfuric acid. And so on and so forth. There's several reactions in the benzene chapter. The key is, though, take your notes here, turn them upside down, put them out of your eyesight, and then look at these lists right here and be like, okay, well, this does this. I cannot draw a benzene ring, and I can't even put the chlorine in the right spot, but that is what is the net result of these reactions. NO2 right here, SO3 right here. And if you forget what that set of reagents does without looking at the table there, skip it, go back to your tables, look at what it does, what it puts on there, and then start over again. When you start over again, don't just do one of them, but list all of them out again. And that way it reinforces those previous reactions as well. You'll also want to go through, in particular, benzene here has other rules, like say, if we had a methyl group right here, a methyl group would be orthopair directing right here because this is an electron donating group. All of our electron withdrawing groups were all meta-directors, and we have very specialty rules for those. For one, we had to watch out with benzene rings having NO2 or any kind of nitrogen on those. Those do not react via Friedel-Crafts. But an electron withdrawing group is basically a carbon that has a positive charge on it, a dipole, or very strong dipole ultimately, or a nitrogen that has a full positive charge on it. in some cases. So these were all metadirectors. And the little trick is there's a lot less metadirectors than there are orthopara directors. So if you have a really good concept of the groups that are electron withdrawing groups, you know those are metadirectors and everything else is orthopara. So, but in this case, you can go through and put an example there for yourself of an electron withdrawing group or electron donating group, and then draw the products in that case too. Here I'm making it a little bit faster here for this video by just sketching it on here, but you would go through with a white sheet of paper, a new white sheet of paper, and go through and list all of those. So okay, that's the memorization method, and especially this time of year, you should go through every single chapter that we've done for the whole year, starting from this semester though. Don't go back to last semester until you've thoroughly reviewed this semester. Then you can go back and review those alkenes, reactions, the reactions of alcohols, etc. All of those chapters. Okay, back to problem number 27 here. This is a type of retrosynthesis problem here where we have a product and the starting material shown. Most of the retrosynthesis is shown in that manner. And when we look at this, we want to make several observations. First, we compare the product to the starting material. The starting material has 1 carbon on it, and the product has 2 carbons on it. 1, 2. So we're going to look through our list and see which set of reagents has added that 1 carbon to that, because we have 1 extra carbon in the product. Excuse me. We also have a fluorine in the para position, which means that we must have at some point had a orthopara director on the ring. And adding a fluorine means that we had a nitro group on there at some point. So a couple of different concepts. This only gets added on there with our specialty reagent that preceded through a diazonium salt. So many students look through these lists here, and you know it's very hard just to write out the synthesis on your own. This is you can see it's a multi-step. One of the hardest you'll probably see on the ACS here, and many of the students will just look through here to see if any of these kind of make sense. And it just looks like a jumble of reactions here, so let's just start out with A here. A, you see, we have a list of reagents, and with this chapter in particular, you can just write out the functional group that gets added in this case. So here we had a NO2, here we made a NH2, then we converted it to a diazonium salt right here, then we made that diazonium salt a fluorine, and oh, and I left out here, the nitro group actually does go into the para position at this point because this methyl group is an electron donating group. Okay, so this looks good so far. I'll sketch it out on the paper if it looks like it is correct. Let's look at these. Here we have the oxidation of a benzylic position right here with this group. Now that one you may have forgotten about. But if you can't remember that one, look at these reagents right here. An alcohol on the top of the arrow with sulfuric acid. This is our only reaction that we have that is actually from the chapter 22. That is the Fischer esterification reaction right there. And we're going to make an ester from that. So here you can see this indeed is an ester. So this reagent, if we forgot about it, actually makes benzoic acids. We do need a carboxylic acid for the ester to react. So even if we couldn't remember from chapter whatever last semester, chapter 12, we can still kind of reason, well, this is the Fischer reaction, So we need a carboxylic acid, so that must have made a carboxylic acid. Sometimes you can use that reasoning. It does indeed do that, so A is the answer. Luckily, we didn't have to go through all the other answer choices. It is still a good idea, though, especially on MCATs, things of that nature, to be able to eliminate all the wrong answers, too. So here, let's go through. Eliminate this one here. This one made a benzoic acid out of that methyl group right there. And then it's trying to add some kind of nucleophilic reaction. We know this is nucleophilic because that is a nucleophile. I don't know if you can see it. That's a negative charge right here on that NH2 right there. But that's a nucleophile, and it needs a halogen on the ring. This is the one that forms benzene. That's when benzene comes out. But we don't want benzene to come out right now. So we're going to mark that off. Next reaction here, dibol H. Dibol H doesn't react with a methyl group. That's ridiculous. Can't believe that's even in there. So we mark that one out. PCC. PCC doesn't react with a methyl group. Stupid answer choices. So we can mark all of those out. And you can see we didn't even have to go to the second reactions. These were so crazy in their nature that we can immediately mark them out. Now, the only reason I knew how to mark those out, though, is I know the functional groups that these react with. Dibol H reacts with various carbonyl compounds right here, and there's no carbonyl present. PCC reacts with OHs, something that has an OH on it. And that is this is a reducing agent. This is an oxidizing agent right here, and you have to know what it reacts with then. And that comes from your reaction tables and going back to your white sheet of paper. These are now, some of these are last semester stuff, but they're very important last semester things that we've gone over and over again. Dibol H makes aldehydes, PCC makes aldehydes, but you have to know what is the starting material. Okay. I've said that like 50 billion times, but hopefully that has been reinforced. Let me go through here and draw this reaction out. I'm going to turn this little benzene around here too and put the methyl group on top. So first we add in nitric acid there. HNO3, H2SO4. That puts a nitro group in the para position. Here we did need to add that functional group to the para position, so this is correct. Nitro group. This is the only way to put a nitrogen on the ring, is to do a nitration of benzene. And then the next step here, H2 gas with palladium catalyst here, will reduce, that's our ultimate reducing agent, is H2 gas. Doesn't reduce the benzene ring because that's a lot less reactive, but it will reduce the NO2 to an NH2. Then when we add this sodium nitrite right here, sodium nitrite, HCl, 0 degrees, that will turn this into a diazonium salt. There's two things we did with the diazonium here. One is the substitution reactions, numerous substitution reactions that should be memorized. It's actually a chloride salt. But it also made azo compound, azo dyes, like we made in the lab. In this case, when we add in this HBF4, it's going to transform. It replaces this N2. The N2 in these reactions is always the leaving group, and it disappears. But it disappears exactly where it is, and the new functional group ends up in the same spot where the N2 was, right there in the para position. Okay, and so now all we have to do is add our potassium permanganate. That will convert the methyl group. It converts benzylic positions here with hydrogens. Note it has to have those hydrogens there. But if we have hydrogens in the benzylic is this one here. It is a sp3 carbon that is attached directly to a benzene ring. It's going to convert that to a carboxylic acid. And then after we do our Fischer reaction here with methanol and H2SO4, usually this is the classic method, we are going to attach that methoxy group to the carbonyl that is right here. Okay, and there's our target molecule.